So in this video we're going over the traveling salesman problem, which is our next project, and it's actually kind of a cool problem. So first off, let's go over what is this problem, what are we trying to do here. So in order to do the traveling salesman problem, what we're going to start off with is a graph with our nodes, and I'm going to label them as capital letters A, B, C, D, and then we have edges connecting all the nodes to every other node within the graph, and I've labeled those with lowercase letters, A, B, C, D, E, F, etc. And you should also assume as part of this problem that it's a weighted graph. So all of these edges have specific weights associated with them. And so in order to understand the traveling salesman problem, we're going to pretend like we're a salesman. And we're starting out at our home base city. And I'm going to say our home base city is A. And what we want to do is we want to travel to all the other cities within our graph so we can explain whatever product we have, right? And as we're going around in our tour of all these different cities, we only want to go to each city once. And we want to make sure that we travel the least amount of distance possible, right? So we want to minimize our time on the road. We don't want to take a lot of road distance. And so that's all the traveling salesman problem is. All we want to do is we want to start off at our home base, visit every other city once, and then minimize the time that we travel on the road before returning back to our home base. And so, as you can see here, there are a couple different options that we could actually do if we were starting off at our home base of A and we wanted to travel to every other city and return back to it. Right? We could go from A to B to C to D and then back to A. Or we could do something like this, A to D to C to B to A. And I'd just like to point out, as part of the problem, going from A to C to D to B to A is no different than going this way around the rectangle, right? Because the road distance is the same, it's just you just went in the backwards order. So we just want to make sure that those are no different, just to clarify. And so in this problem, right, it's pretty simple, right? There are only a couple different ways that we can make it around all our nodes. But as you might see in the project documentation, as the number of cities or number of nodes gets larger, well, the number of these things called tours, something that gets us all the way around, becomes exponentially greater. So I think they said for a grouping of like 25 nodes, it would take like millions of years to actually look for every single unique combination and test it. And so that's a big issue, right? We can't solve by just looking for each of those different tours. And so what we have to do is we have to come up with constraints. And that's where we're going to be using in-min-prog and this idea of integer programming again. And so if we think about the problem a little bit more, we can actually come up with these constraints. And so what we can realize is that if we only want to travel to the city once, only two of the edges associated with that city can be activated as a part of our constraints, right? Because let's say we're looking at city A, right? If we travel to city A once, maybe we use edge B to go to it and then edge F to leave it. If we ever use edge A again when we're trying to find this optimum tour, well, that means we've returned back to A, and that breaks the problem. And so our constraints really boil down to is we only use two of the given edges for any given node, and that prevents us from returning back to that given node. And so here are the constraints. I'm just going to give a couple examples. Again, for A, we can see that edges A, B, and F have to be equal to 2. Again, that means we're only using two of the edges associated with A, and that prevents us from returning back to A. For B, we have edges A, D, and E. A, D, and E. And once again, that's saying we can only use two of the edges of B. That prevents us from returning back to it and breaking the problem. And so what you're going to be doing is you're actually going to be using our AEQ matrix, which we worked with last week, and that's our edge incidence matrix. And so that'll allow you to construct these statements. And then basically what you're going to do is you're going to plug it into in-min-prog. And that's just going to be the cookie cutter idea that we had last week, where it's just going to be figuring out your upper bound, your lower bound, AEQ, all that stuff, and you're going to plug it in. And so what turns out is even when we do this, all these constraints, and we plug it into in-min-prog, we come up with a secondary problem. And this problem is subtours. And so I've drawn another graph, and I first want to say that this graph is not in any way related to this graph. This is just an example I've pulled off the project documentation in order to help you understand it. And so basically what happens is if we make all these constraints for a given graph, we plug it into in-min-prog, we come up with things like this. MATLAB has mistakenly broken down our graph into many little tours and these subtours. And so obviously this is not what we want, right? If we start off at this node, we can't reach to every other node, right? We can't complete the salesman problem correctly. And so we have to figure out how do we eliminate these subtours, right? We want to get rid of these and so we can actually solve the problem correctly. And that's where we can use something called concomp. Basically, concomp is another MATLAB function that's going to tell us which nodes are involved in which subtours of the graph. So basically say, oh look, these nodes are all involved in that one subtour and these nodes are all involved in that subtour. So we can use this tool concomp in order to figure out the constraints we need to build in order to actually eliminate the subtours. And so I've drawn a couple of the examples of actual subtour elimination constraints so you can understand what we're doing when we're building these elimination constraints. And so basically what happens is for this subtour, basically say edges A, B, and C have to be less than or equal to 2. And then for this one, edges D, E, and F have to be less than or equal to 2. And so what it really boils down to is we take the number of nodes within a given subtour and we subtract 1. That's how we get these two values here for our constraints. And essentially what we're going to be doing within this project is we're going to be doing a while loop. And we're going to add one of these constraints every single time that we redo int minprog, and we're going to subtract out one of these subtours at a time. So what's going to happen is we're going to say on our first iteration of the while loop, we're going to build this first constraint, and then we're going to subtract out this subtour. Then our next iteration, we're going to add in this additional constraint, and then we're going to eliminate both of the subtours, and then we're going to finally have solved the traveling salesman problem. We're going to get that big loop with the minimum distance traveled. And so yeah, that's this week's project. And just to give a little bit more information about the project, it's pretty simple. All you're doing is you're taking another .txt file, you're going to read it off, build the proper matrices you're going to need as like helper matrices, so that might be like your adjacency matrix and of course your edge incidence matrix. You're going to first build the constraints without considering subtours at all. You're going to build them up, and you're going to use inlinprog, and then you're going to visualize all the subtours, right? We're going to see the errors that actually appear. We're going to see that subtours are an issue, and we're going to have to figure out how to eliminate them. And then once you see these subtours, what you're going to do is you're going to use concomp in order to figure out which subtours and which nodes are part of those subtours. And then you're going to use a while loop, and you're going to build one elimination constraint at a time, and you're going to subtract off one subtour at a time until finally we reach that point where we've completed the traveling salesman problem. So I hope this video has helped, and I'll see you guys in the next one.